Can we search for life on Venus? We're heading to a world that has long been dismissed as a hellish wasteland. Yet recent discoveries have transformed it into one of the most compelling targets in astrobiology. This question has ignited passionate debates in scientific circles, sparked revolutionary mission designs, and challenged our fundamental assumptions about where life might exist in our solar system. If you find solace in these gentle explorations of space science, I'd be deeply grateful if you'd consider subscribing and giving this video a like. Your support fuels these late-night journeys through the mysteries of our universe. The visuals are here to accompany our cosmic voyage, but please feel free to close your eyes, settle into comfort, and let your imagination drift among the clouds of our neighboring world. I'd also love to know where you're joining me from tonight. Drop a comment with your time and location below. Are you watching the evening stars emerge in your corner of Earth? Or perhaps dawn is breaking where you are, painting your sky with the same light that illuminates Venus in our morning or evening sky. There's something beautifully poetic about contemplating the possibility of life on Venus while we're scattered across our own living planet, each under the same celestial dome that has witnessed billions of years of cosmic evolution. Venus has always been a world of contradictions, a planet that simultaneously fascinates and terrifies us. Named after the Roman goddess of love and beauty, Venus appears as a brilliant jewel in our sky, the third brightest object after the Sun and Moon. Yet beneath its gleaming cloud cover lies a surface hot enough to melt lead, with crushing atmospheric pressure and sulfuric acid rain. For decades, scientists wrote off Venus as utterly hostile to life. But science has a wonderful way of surprising us, of forcing us to reconsider our assumptions and expand our understanding of what's possible. Our story begins with the discovery that sent shockwaves through the scientific community and reignited interest in Venus exploration after decades of relative neglect. In September 2020, a team of astronomers led by Jane Greaves at Cardiff University announced something extraordinary. Using sophisticated telescopes on Earth, they had detected phosphine gas in the atmosphere of Venus. This might sound like a technical detail, but it represented a potential game changer in our search for extraterrestrial life. Phosphine is a simple molecule consisting of one phosphorus atom bonded to 3 hydrogen atoms. On Earth, this gas is primarily produced by living organisms, particularly anaerobic bacteria thriving in oxygen-poor environments like swamps, marshes, and even in the digestive systems of some animals. While phosphine can be produced through industrial processes, in nature it serves as what scientists call a biosignature, a chemical fingerprint that might indicate the presence of life. The detection of phosphine in Venus's atmosphere was startling because scientists couldn't identify any known non-biological process that could produce this gas in the quantities observed. The researchers carefully considered alternative explanations. Could volcanic activity create phosphine? Could lightning strikes generate it? Could meteorite impacts or other geological processes account for its presence? After exhaustive analysis, they found no adequate non-biological explanation for the phosphine they observed. The announcement triggered an immediate and intense scientific debate that continues to this day. Some researchers question the detection itself, suggesting that the signal might be contaminated by other gases, or that data processing errors could have created a false positive. Others argued that the phosphine signal was actually sulfur dioxide, a gas commonly found in Venus's atmosphere. The controversy highlighted the extraordinary challenges of detecting potential biosignatures from millions of miles away, and the rigorous skepticism that rightfully accompanies such extraordinary claims. As the debate raged, additional observations were made, and the story became more complex. Some follow-up studies failed to detect phosphine at the levels initially reported, while others found weaker but still present signals. The scientific process was working exactly as it should, with multiple teams using different instruments and methods to verify or challenge the initial findings. This ongoing investigation exemplifies the careful, methodical approach required when we're potentially on the verge of one of the most significant discoveries in human history. But the Phosphine story took another dramatic turn in 2024. Dave Clements and his team at Imperial College London announced new findings based on years of additional observations and data analysis. Not only did they confirm the presence of phosphine in Venus's atmosphere, albeit at lower concentrations than initially reported, but they also detected ammonia, another molecule that on Earth is primarily associated with biological processes. The detection of multiple potentially biological gases strengthened the case that something unusual was happening in Venus's atmosphere, even if scientists couldn't yet determine whether that something was life or unknown chemistry. To understand why these discoveries are so significant, we need to appreciate just how extreme Venus truly is. At the surface level, Venus presents conditions that would instantly destroy any known form of life. Temperatures reach 737 Kelvin, which translates to a scorching 464 degrees Celsius or 867 degrees Fahrenheit. The atmospheric pressure at the surface is 92 to 95 times greater than Earth's sea level pressure, creating an environment where the atmosphere behaves more like a supercritical fluid than a gas. The surface is hot enough to melt lead, zinc, and tin, making it one of the most hostile environments in our solar system. These extreme conditions result from a runaway greenhouse effect that transformed Venus from what might once have been an Earth-like world into the inferno we observe today. Venus's thick atmosphere, composed of 96.5% carbon dioxide, traps solar radiation with devastating efficiency. The greenhouse effect on Venus is so extreme that the night side of the planet, which receives no direct sunlight, remains nearly as hot as the day side. This hellish environment makes the Venusian surface completely uninhabitable by any Earth-based life forms we know of. But here's where the story becomes fascinating. While Venus's surface is utterly hostile, conditions in the planet's upper atmosphere tell a remarkably different story. Between altitudes of approximately 48 to 70 kilometers above the surface, we find an environment that's surprisingly Earth-like in some important ways. In this atmospheric region, temperatures range from 30 to 80 degrees Celsius, which, while warm, falls within the range that some extremophile organisms on Earth can tolerate. The atmospheric pressure in this zone is roughly equivalent to Earth's surface pressure, eliminating the crushing conditions found below. This upper atmospheric region represents what scientists call the habitable zone of Venus, a layer of clouds where conditions might potentially support some form of life. The discovery that Venus has atmospheric conditions comparable to Earth's surface came as a surprise to many people who think of Venus only in terms of its hellish surface environment. It's in this temperate zone of Venus's atmosphere where the controversial phosphine and ammonia detections were made. adding to the intrigue surrounding the possibility of aerial life. However, even in this more temperate atmospheric zone, potential life would face extraordinary challenges unknown on Earth. Venus's clouds are composed primarily of concentrated sulfuric acid, creating an environment that's orders of magnitude more acidic than the most extreme acid environments where life has been found on our planet. The scarcity of water in Venus's atmosphere presents another significant challenge, as water is considered essential for life as we know it. Any hypothetical Venusian life would need to evolve biochemistry radically different from terrestrial organisms. While Venus's cloud conditions are more extreme than most terrestrial environments, the existence of such hardy organisms provides biological precedent for life in seemingly impossible conditions. These discoveries have expanded our understanding of life's boundaries and suggest that the envelope of habitability might be far broader than we once imagined. They remind us that life, at least as it has evolved on Earth, is remarkably tenacious and creative in finding ways to survive and thrive in extreme environments. The search for life on Venus is entering an unprecedented era of exploration, with multiple space missions planned that will provide direct investigation of the planet's atmosphere and surface. These missions represent a renaissance in Venus exploration after decades of relative neglect in favor of Mars and the outer solar system. The convergence of renewed scientific interest, technological advances, and the tantalizing possibility of discovering life has transformed Venus from a largely overlooked world into one of the highest priority targets for planetary exploration. The most imminent mission in this new wave of Venus exploration is the Venus Life Finder, a privately funded endeavor that represents a revolutionary approach to planetary science. Developed through an innovative collaboration between Rocket Lab and the Massachusetts Institute of Technology, this mission embodies a new philosophy of space exploration, one that prioritizes focused scientific objectives over comprehensive but expensive flagship missions. Originally planned for launch in May 2023, the Venus Life Finder is now scheduled to launch no earlier than summer 2026, carrying with it the hopes and dreams of scientists who have waited decades for direct investigation of Venus's potentially habitable clouds. What makes the Venus Life Finder truly remarkable is not just its scientific mission, but its approach to making planetary exploration more accessible and cost-effective. With a total mission cost estimated at less than $10 million, funded by Rocket Lab, MIT, and undisclosed philanthropists, this mission costs a fraction of what traditional planetary missions require. Compare this to NASA's upcoming Venus missions, each carrying price tags of approximately $500 million, and you begin to appreciate the revolutionary potential of this approach. The Venus Life Finder demonstrates that meaningful scientific discovery doesn't always require massive budgets and decades-long development cycles. The spacecraft itself is a marvel of engineering miniaturization, a 17-kilogram cone-shaped atmospheric probe measuring just 40 centimeters across. Despite its compact size, this probe carries sophisticated scientific instrumentation designed specifically for the challenging task of detecting potential biosignatures in Venus's acidic clouds. The single scientific instrument aboard the probe is the autofluorescence nephelometer, a device that will project a 440 nanometer diode laser into the Venusian atmosphere during the probe's brief but crucial descent through the cloud layers. The operating principle of this instrument is elegantly simple yet scientifically profound. As the probe descends through Venus's atmosphere, cloud particles will pass through the laser beam, causing light to scatter in patterns that reveal information about the particle's size, shape, and concentration. More importantly, if organic molecules are present in cloud particles, these fluoresce when struck by the laser light, essentially glowing with a characteristic signature that the instrument can detect and record. This fluorescence would provide compelling evidence of organic chemistry occurring in Venus's atmosphere, a discovery that would revolutionize our understanding of the planet's potential habitability. However, the technical challenges facing the Venus Lifefinder mission are immense, reflecting the harsh realities of Venus exploration. The probe will enter Venus's atmosphere on the planet's night side to minimize background light interference with its sensitive optical measurements. During atmospheric entry, the probe will experience crushing deceleration forces of up to 60 times Earth's gravity, testing the limits of its robust construction. Unlike missions to Mars, which can deploy parachutes to slow their descent, the Venus Lifefinder will plunge through the atmosphere without any deceleration system, relying on its brief transit time through the cloud layers to complete its measurements. The mission timeline is breathtakingly compressed, highlighting the intense operational demands of Venus exploration. The probe will have just 5 precious minutes in the cloud layer between 65 and 45 kilometers altitude to perform its life detection measurements. During this brief window, every second counts as the instrument collects data that could potentially answer one of humanity's most profound questions. After completing its measurements, the probe must immediately transmit its findings to Earth before continuing its descent to impact the Venusian surface approximately 30 minutes after atmospheric entry. The data transmission challenges add another layer of complexity to this already demanding mission. Due to constraints on transmitter power and the limited time available for communication, the probe will send its data through a channel with only 125 bytes per second bandwidth. To put this in perspective, this is roughly equivalent to the data rate of early dial-up internet connections from the 1990s. Given these severe bandwidth limitations, the mission team has developed sophisticated data compression techniques and neural network algorithms trained on laboratory measurements and theoretical calculations to extract maximum scientific value from every bit of transmitted information. The Venus Lifefinder represents just the beginning of what promises to be the most intensive period of Venus exploration in human history. NASA's ambitious Venus exploration program includes 2 major missions that will provide comprehensive study of the planet from multiple perspectives. The Da Vinci mission, whose name stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging, is scheduled to launch in the early 2030s and will explore Venus with both an orbiting spacecraft and an atmospheric descent probe. Da Vinci will achieve several groundbreaking firsts in Venus exploration that will complement and extend the findings of the Venus Lifefinder mission. The mission will be the first to closely explore Alpha Regio, a highland region known as a tessera, representing some of the oldest and most geologically complex terrain on Venus. These ancient surfaces, found only on Venus, may preserve rocks that are billions of years old, offering scientists unprecedented access to Venus's early geological history and potential clues about the planet's past habitability. The Da Vinci Descent probe will capture the first close-up images of Venus's surface in more than 4 decades, providing visual documentation of the planet's ridged and complex terrain. More importantly, from an astrobiological perspective, Da Vinci will be the first mission to analyze the chemical composition of Venus's lower atmosphere through continuous measurements taken at regular intervals during descent. This chemical analysis will begin approximately 90,000 feet above the surface and continue until just before impact, providing detailed information about gases and chemical compounds that may originate from Venus's lower clouds, surface, or even subsurface environments. The companion Veritas mission, standing for Venus Emissivity, Radioscience in SAR, Topography and Spectroscopy, will provide comprehensive orbital mapping of Venus using advanced radar systems. Veritas will map Venus's surface with at least 3 times better resolution than NASA's Magellan spacecraft, which orbited Venus nearly 30 years ago and provided our current best understanding of the planet's surface geology. This detailed mapping will be crucial for understanding Venus's geological evolution and identifying potential sites of ongoing volcanic activity that could influence atmospheric chemistry. However, the Veritas mission has faced significant budgetary challenges that highlight the ongoing struggles for planetary science funding. Originally scheduled to launch in 2027 to inaugurate what scientists hoped would be the Decade of Venus, Veritas has been delayed to no earlier than 2031. Budget constraints have placed the mission in what administrators euphemistically call deep freeze, with funding held at minimal levels that barely maintain the mission's viability, while other priorities compete for limited NASA resources. Europe's contribution to this renaissance in Venus exploration comes through the Envision mission, developed by the European Space Agency and scheduled to launch in 2031 or later. Envision is designed to provide a holistic view of Venus from its inner core to upper atmosphere, working in coordination with NASA's Da Vinci and Veritas missions to create the most comprehensive study of Venus ever undertaken. The mission will focus on understanding how and why Venus and Earth, which began as remarkably similar worlds, evolved along such dramatically different paths. The scientific instruments being developed for these Venus missions represent cutting-edge technology specifically designed for the extreme challenges of Venus exploration. The autofluorescence nephelometer aboard the Venus Life Finder exemplifies the innovative approaches required for biosignature detection in such a hostile environment. As the probe flies through Venus's cloud region, this instrument will shine its laser through a tiny window, striking molecules in the Venusian clouds and analyzing the scattered and fluorescent light to measure molecular concentrations, sizes, and shapes. The detection of organic compounds in Venus's atmosphere would represent a monumental scientific breakthrough, though scientists are careful to emphasize that such a discovery would not constitute conclusive proof of life. The presence of organics would indicate that Venus harbors intriguing chemical activity within its clouds, potentially including biological processes, but could also result from previously unknown atmospheric chemistry. As one researcher noted, the detection of fluorescence would tell us that something incredibly interesting is occurring in Venus's clouds, even if we couldn't immediately determine whether that something represents life or exotic chemistry. The field of astrobiology has developed sophisticated frameworks for interpreting potential biosignatures and distinguishing them from non-biological processes that might mimic signs of life. This recognition has led to more rigorous standards for evaluating potential biosignatures, requiring comprehensive environmental context and multiple lines of evidence before concluding that life might be responsible for observed chemical signatures. Modern life detection techniques increasingly incorporate artificial intelligence and machine learning approaches that can identify subtle patterns in data that might escape human analysis. These advanced computational methods are being developed specifically for planetary exploration missions, where the limited data transmission capabilities and extreme environmental conditions require maximum extraction of scientific information from minimal datasets. Neural network analysis has already demonstrated remarkable success in identifying potential biosignatures in terrestrial environments, suggesting enormous potential for application to extraterrestrial life detection. The search for life on Venus also benefits from Earth-based analog studies that help scientists understand how life might survive in extreme environments similar to those found in Venus's clouds. Specialized facilities like the Glenn Extreme Environments Rig at NASA's Glenn Research Center have been constructed to partially reproduce Venus's atmospheric conditions, including the chemical composition, temperature, and pressure found in the planet's potentially habitable cloud layers. These analog studies provide crucial insights into the challenges and possibilities for life in Venus-like environments. As we stand on the threshold of this new era in Venus, for life beyond Earth requires exploration. We're reminded that the search, not just advanced technology and substantial funding, but also the courage to challenge our assumptions about where life might exist. Venus has taught us that habitability might be found in the most unexpected places, that life's boundaries may extend far beyond what we once thought possible. The upcoming missions to Venus represent more than just scientific expeditions. They embody humanity's relentless curiosity and our determination to answer one of the most profound questions we can ask. Are we alone in the universe? The implications of discovering life on Venus would reverberate far beyond the scientific community, fundamentally altering our understanding of biology itself and our place in the cosmic order. Such a discovery would demonstrate that life can emerge and thrive in environments radically different from Earth, expanding the potential habitable zones throughout our galaxy by orders of magnitude. If organisms can survive in the sulfuric acid clouds of Venus, floating through an atmosphere devoid of solid surfaces, then the number of potentially habitable worlds in our universe suddenly becomes almost incomprehensibly vast. Consider for a moment the profound philosophical implications of aerial life drifting through Venus's temperate cloud layers. These hypothetical organisms would represent a form of existence entirely alien to terrestrial biology, never touching solid ground, never experiencing the stability of a planetary surface, existing instead in perpetual flight through acidic skies. Their entire evolutionary history would unfold in 3 dimensions rather than the surface-bound existence we know on Earth. Such life would challenge our most fundamental assumptions about what organisms require to survive and thrive. The biochemistry of potential Venusian life forms presents fascinating puzzles that push the boundaries of our understanding. Instead of water serving as the universal solvent for biological processes, these organisms might have evolved to use concentrated sulfuric acid as their medium for life. Their cellular structures, if they possess anything analogous to cells, would need to be fundamentally different from terrestrial life, perhaps utilizing entirely novel molecular frameworks that we've never encountered or even imagined. Scientists have begun to envision what such exotic biochemistry might look like, drawing inspiration from extremophile research on Earth, while acknowledging that Venusian life would likely surpass even our planet's most hardy organisms in their adaptation to extreme conditions. These theoretical organisms might derive energy from the chemical gradients present in Venus's atmosphere, perhaps processing sulfur compounds in ways that terrestrial life cannot. They might have evolved mechanisms to concentrate and utilize the trace amounts of water vapor present in the clouds. Or perhaps they've discovered entirely water-free approaches to sustaining complex chemistry. The possibility of photosynthesis in Venus's clouds adds another layer of intrigue to these speculations. While the planet's thick atmosphere filters much of the solar radiation that reaches the cloud layers, sufficient energy might still be available to power photosynthetic processes. However, any such process would need to function in the complete absence of liquid water and in the presence of highly corrosive sulfuric acid, requiring evolutionary innovations beyond anything we observe in terrestrial photosynthesis. The detection methods being developed for Venus missions must account for these exotic possibilities while remaining sensitive enough to identify subtle biosignatures that might differ dramatically from terrestrial life. The autofluorescence techniques employed by the Venus Life Finder mission represent just one approach to this challenge. Future missions might carry mass spectrometers capable of identifying complex organic molecules, or sophisticated cameras designed to detect organized structures that might indicate biological activity. The challenges of sample return from Venus highlight the extraordinary technical demands of studying this hostile world. Unlike Mars missions, where rovers can leisurely examine rocks and soil samples over months or years, Venus missions must accomplish their scientific objectives during brief encounters with the planet's atmosphere. The extreme conditions make it impossible to deploy long-term surface missions, and even atmospheric probes face severe constraints on their operational lifetime. Future Venus exploration might require innovative approaches that we're only beginning to imagine. Concept studies have explored the possibility of floating research stations that could maintain position in Venus's temperate cloud layers for extended periods, powered by solar panels and equipped with comprehensive life detection instruments. These aerial platforms would face immense engineering challenges, from designing materials that can withstand prolonged exposure to sulfuric acid to developing power systems that function reliably in Venus's unique atmospheric environment. The international collaboration emerging around Venus exploration reflects the global significance of this scientific endeavor. While NASA and ESA lead major mission development efforts, space agencies from India, Japan, and Russia have all expressed interest in Venus exploration. This collaborative approach ensures that multiple perspectives and technologies contribute to our understanding of Venus, maximizing the scientific return from this challenging but potentially revolutionary field of study. The timeline for Venus exploration stretches across the next 2 decades, with missions launching throughout the 2020s and 2030s, creating an unprecedented observational campaign. The Venus Life Finder mission will provide our first direct search for biosignatures in Venus's atmosphere, followed by the comprehensive investigations of Da Vinci, Veritas, and Envision. Together, these missions will transform Venus from one of the least understood planets in our solar system to one of the most thoroughly studied. The data collected by these missions will require years of analysis and interpretation as scientists work to understand the complex chemical processes occurring in Venus's atmosphere and determine whether any of these processes might be biological in origin. The phosphine and ammonia detections that sparked renewed interest in Venus will be just the beginning of a comprehensive chemical inventory of the planet's atmospheric composition. Advanced computational models are being developed to simulate Venus's atmospheric chemistry and help scientists distinguish between biological and non-biological explanations for observed chemical signatures. These models incorporate everything from photochemistry, driven by solar radiation, to potential volcanic outgassing and meteorite impacts, creating comprehensive frameworks for interpreting observational data. The search for life on Venus also connects to broader questions about planetary evolution and habitability. Understanding how Venus transformed from a potentially habitable world to its current extreme state provides crucial insights for evaluating the long-term stability of planetary climates. This research has direct relevance for understanding Earth's climate system and assessing the habitability of exoplanets discovered around other stars. Venus serves as a natural laboratory for studying runaway greenhouse effects, atmospheric evolution, and the boundaries of planetary habitability. The lessons learned from Venus exploration will inform our understanding of climate dynamics on Earth and help us evaluate the potential habitability of the thousands of exoplanets being discovered by space-based telescopes. The technological innovations developed for Venus missions often find applications in other areas of space exploration and terrestrial science. The extreme environment instrumentation designed for Venus can be adapted for studying other challenging environments, from the deep ocean to volcanic systems on Earth. The miniaturization techniques pioneered by missions like the Venus Life Finder demonstrate new approaches to space exploration that prioritize efficiency and cost-effectiveness. As we look toward the future of Venus exploration, we can envision increasingly sophisticated missions that build upon the foundation laid by current projects. Advanced atmospheric probes might carry comprehensive life detection suites, including DNA sequencing capabilities and microscopic imaging systems. Orbital missions could deploy networks of small atmospheric probes to study chemical variations across different regions of Venus's clouds. The possibility of eventually establishing a permanent research presence in Venus's atmosphere, while technically daunting, represents an intriguing long-term goal for human space exploration. Such missions would require revolutionary advances in materials science, life support systems, and spacecraft design. But they could provide unprecedented opportunities for detailed study of Venus's atmospheric chemistry and potential biology. The search for life on Venus embodies humanity's relentless curiosity about our place in the universe and our determination to explore even the most challenging environments in pursuit of knowledge. Whether or not we ultimately discover life in Venus's clouds, the journey of exploration itself expands our understanding of planetary science, atmospheric chemistry, and the remarkable diversity of environments that exist within our solar system. Every mission to Venus, every measurement of atmospheric composition, every analysis of chemical signatures contributes to our growing understanding of this enigmatic world. The planet that once seemed utterly hostile and barren now reveals itself as a complex, dynamic system where unexpected chemistry occurs in the space between its hellish surface and the cold vacuum of space. As you drift deeper into contemplation of these cosmic possibilities, remember that Venus hangs in our sky as a brilliant beacon, sometimes gracing our morning hours as the dawn star, sometimes illuminating our evenings as the first light to emerge from twilight's embrace. Within that shining point of light lies a world of mysteries waiting to be unraveled, potential discoveries that could reshape our understanding of life itself, and answers to questions that have tantalized humanity since we first looked up and wondered what secrets the planets might hold. The convergence of these multiple Venus missions in the coming decade creates an unprecedented opportunity to answer fundamental questions about the nature of life and habitability in our solar system. Each mission brings unique capabilities and perspectives, forming a comprehensive investigative network that will peer into Venus's secrets from multiple vantage points simultaneously. The Venus Life Finder will provide our first direct taste of the planet's atmospheric chemistry, while Da Vinci descends through layers of cloud and gas, measuring compositions that have remained hidden for billions of years. Veritas will map the surface with radar precision, revealing geological stories written in stone and metal, while Envision provides the orbital perspective that ties surface and atmosphere together in a complete planetary portrait. This coordinated approach represents a fundamental shift in how we explore other worlds. Rather than relying on single missions separated by decades, we're entering an era of simultaneous complementary investigations that will generate data faster than ever before. The scientific community is preparing for an avalanche of discoveries, developing new analytical techniques and theoretical frameworks to handle the wealth of information these missions will provide. The atmospheric chemistry of Venus presents puzzles that extend far beyond simple questions of habitability. The planet's clouds contain trace amounts of water vapor, but nowhere near the concentrations we associate with terrestrial life. Scientists have calculated that any hypothetical organisms in Venus's atmosphere would need to maintain water concentrations within their bodies that are hundreds of times higher than the surrounding environment. This would require biological mechanisms unlike anything we observe on Earth, perhaps involving specialized cellular structures that can extract and concentrate water from the acidic atmosphere. The energy sources available to potential Venusian life forms present equally fascinating challenges. Solar radiation penetrates Venus's thick clouds in significantly reduced amounts, creating a dimly lit environment even in the planet's daytime hours. Any photosynthetic processes would need to operate with remarkable efficiency, perhaps utilizing wavelengths of light that terrestrial plants cannot process. Alternatively, chemosynthetic pathways might dominate, drawing energy from the complex chemical reactions occurring naturally in the planet's dynamic atmosphere. Recent laboratory experiments have revealed surprising possibilities for organic chemistry in environments previously thought to be utterly hostile to complex molecular processes. Researchers have discovered that certain organic compounds can remain stable in concentrated sulfuric acid for extended periods, and some can even undergo sophisticated chemical transformations that create more complex structures. These findings suggest that Venus's acidic environment might not be the absolute barrier to life that scientists once assumed. The vertical structure of Venus's atmosphere creates distinct chemical zones, each with its own unique conditions and potential for harboring different types of chemical processes. The upper haze layers, extending from about 60 to 80 kilometers above the surface, contain the highest concentrations of sulfuric acid and represent the most challenging environment for any form of life. Below this region lies the main cloud deck, where temperatures and pressures are more moderate and where the controversial phosphine and ammonia detections were made. Deeper still, approaching the lower boundary of the clouds, conditions become increasingly extreme as temperatures rise and pressures mount. This lower atmospheric region may hold clues about chemical exchanges between the surface and the atmosphere, processes that could influence the overall chemistry of the cloud layers above. Understanding these vertical gradients will be crucial for interpreting the data collected by atmospheric probes during their brief descent through Venus's layered atmosphere. The temporal dynamics of Venus's atmosphere add another dimension of complexity to the search for life. The planet experiences global atmospheric circulation patterns that transport chemical compounds across vast distances, mixing materials from different altitudes and latitudes. These circulation patterns could potentially distribute any biological signatures throughout the atmosphere, making detection more likely, but also complicating efforts to identify the original sources of interesting chemical signatures. Venus's atmospheric chemistry also varies with the planet's day-night cycle, though this cycle operates on a timescale utterly foreign to Earth-based life. Venus rotates so slowly that a single day on the planet lasts longer than its year, creating extreme variations in solar heating and atmospheric dynamics. The night-side atmosphere experiences different chemical processes than the day-side, potentially creating temporal variations in atmospheric composition that future missions will need to account for. The search for life on Venus has also sparked renewed interest in theoretical astrobiology, the study of what life might look like under conditions radically different from those on Earth. Scientists are developing new models of cellular structure and metabolism that could function in highly acidic environments, exploring possibilities that push the boundaries of biochemistry into previously uncharted territory. These theoretical investigations help guide the design of detection instruments and inform the interpretation of observational data. One particularly intriguing possibility involves the concept of aerial plankton, microscopic organisms that might drift through Venus's atmosphere, much like marine plankton drift through Earth's oceans. Such organisms would need to maintain neutral buoyancy in the dense Venusian atmosphere, perhaps through specialized gas-filled structures or unique cellular compositions. They might form complex ecological relationships, with different species occupying different atmospheric niches and potentially even exhibiting migratory behaviors that follow atmospheric circulation patterns. The challenges of confirming biological signatures in Venus's atmosphere extend far beyond initial detection. Even if missions successfully identify organic compounds or other potential biosignatures, scientists will need to rule out numerous non-biological explanations. Volcanic outgassing could potentially produce complex organic molecules. Meteorite impacts might deliver organic compounds from space, and unknown photochemical processes driven by solar radiation could create organic signatures through purely abiotic means. The scientific community has learned valuable lessons from previous claims of extraterrestrial life that were later explained by non-biological processes. The famous meteorite ALH 84001, once thought to contain fossilized Martian microbes, taught scientists about the importance of considering alternative explanations and requiring multiple independent lines of evidence before reaching extraordinary conclusions. The Phosphine controversy surrounding Venus demonstrates that these lessons remain highly relevant to contemporary astrobiology. Advanced analytical techniques being developed for Venus missions incorporate sophisticated statistical methods and machine learning algorithms designed to distinguish subtle biological signatures from the complex background of atmospheric chemistry. These computational approaches can identify patterns in chemical data that might escape human analysis, potentially revealing biosignatures that are embedded within larger datasets of atmospheric measurements. The international scientific collaboration surrounding Venus exploration extends beyond government space agencies to include private companies, academic institutions, and citizen science initiatives. This broad participation ensures that diverse perspectives and innovative approaches contribute to our understanding of Venus, maximizing the scientific return from missions while fostering global cooperation in the search for extraterrestrial life. The implications of discovering life on Venus would extend far beyond confirming the existence of extraterrestrial organisms. Such a discovery would provide our first example of how life might evolve under conditions dramatically different from those on Earth, offering insights into the fundamental principles of biology and the potential diversity of life throughout the universe. The biochemical innovations required for survival in Venus's acidic atmosphere could inspire new approaches to biotechnology and materials science. Venus exploration also serves as a testing ground for technologies and techniques that will be essential for studying potentially habitable exoplanets. The challenges of detecting biosignatures in Venus's atmosphere mirror those faced when analyzing the atmospheric composition of planets orbiting other stars. Success in characterizing Venus's atmospheric chemistry will demonstrate our readiness to interpret similar data from exoplanetary observations. The ongoing development of increasingly sensitive detection methods promises to revolutionize our ability to search for life throughout the solar system. Techniques pioneered for Venus missions could be adapted for studying the subsurface oceans of Europa and Enceladus, the methane lakes of Titan, or the ancient riverbeds of Mars. Each technological advancement brings us closer to answering the fundamental question of whether life exists beyond Earth. The philosophical implications of discovering life on Venus would be particularly profound given the planet's extreme conditions. If organisms can thrive in the sulfuric acid clouds of our neighboring world, it would suggest that life might be far more common throughout the universe than we currently imagine. Every star system containing planets might harbor multiple worlds with the potential for life, even if those worlds appear utterly hostile from our terrestrial perspective. As we stand on the threshold of this new era in Venus exploration, we're reminded that the greatest discoveries often come from the most unexpected places. Venus, dismissed for decades as a dead world, now emerges as one of the most promising targets in our search for extraterrestrial life. The planet that once represented the limits of habitability now expands our understanding of where life might exist, challenging us to think beyond our earthbound assumptions about what organisms require to survive and flourish. The missions preparing to explore Venus carry with them the hopes and dreams of scientists who have dedicated their careers to understanding this enigmatic world. They represent humanity's relentless curiosity and our determination to explore even the most challenging environments in pursuit of knowledge. Whether these missions ultimately discover signs of life or reveal new forms of exotic chemistry, they will transform our understanding of Venus and expand our appreciation for the remarkable diversity of worlds that exist within our cosmic neighborhood. As you contemplate these possibilities, drifting peacefully through your own thoughts like hypothetical organisms might drift through Venus's temperate clouds, remember that we live in an extraordinary time. We are the first generation of humans with the technology and knowledge necessary to seriously search for life on other worlds. The questions we're asking about Venus, the missions we're launching, and the discoveries we're making will echo through history, shaping how future generations understand their place in the vast cosmic web of existence. Venus continues to beckon to us from across the void, its brilliant presence in our sky a constant reminder of the mysteries that await our investigation. In its swirling clouds and hidden chemistry, in its extreme conditions and unexpected possibilities, Venus embodies the profound truth that the universe is far stranger and more wonderful than we dare to imagine. The search for life on Venus has also illuminated fundamental questions about how we define life itself and what we consider to be the minimal requirements for biological processes. Traditional definitions of life rely heavily on Earth-based examples, emphasizing liquid water, carbon-based chemistry, and specific temperature ranges. But Venus challenges us to expand these definitions, to consider whether life might utilize entirely different chemical foundations while still maintaining the essential characteristics we associate with living systems. The concept of metabolism takes on new dimensions when we consider the chemical environment of Venus's clouds. Terrestrial metabolism relies on carefully orchestrated chemical reactions that extract energy from food sources and use that energy to maintain cellular structures and processes. In Venus's acidic atmosphere, hypothetical organisms might have evolved metabolic pathways that utilize the abundant sulfur compounds as energy sources, perhaps processing sulfuric acid itself as both a medium and a metabolic substrate. These metabolic possibilities extend into fascinating territory when we consider the potential for symbiotic relationships in Venus's atmospheric ecosystem. Just as terrestrial environments often support complex webs of interdependent organisms, Venus's clouds might harbor communities of different species that have evolved complementary metabolic strategies. Some organisms might specialize in processing certain atmospheric compounds, while others utilize the waste products of their neighbors, creating closed-loop systems that maximize the efficiency of resource utilization in this resource-limited environment. The reproductive strategies of potential Venusian life forms present equally intriguing puzzles. Without solid surfaces for attachment or nest building, aerial organisms would need to develop entirely airborne methods of reproduction and development. Perhaps they might form temporary aggregations during reproductive cycles, creating brief but complex social structures that dissolve once reproduction is complete. Or they might have evolved broadcast reproduction strategies, releasing reproductive cells into the atmospheric currents to drift until they encounter suitable conditions for development. The sensory capabilities required for survival in Venus's three-dimensional atmospheric environment would likely differ dramatically from those of surface-dwelling terrestrial organisms. These aerial life forms might have evolved sophisticated chemical sensing abilities to navigate the complex gradients of acidity, temperature, and chemical composition that vary throughout the cloud layers. They might detect subtle changes in atmospheric circulation patterns, using these cues to maintain position within favorable atmospheric zones. The evolutionary history of any potential Venusian life forms raises profound questions about the planet's past habitability. Current models suggest that Venus might have maintained liquid water oceans for billions of years before the runaway greenhouse effect transformed it into its current extreme state. If life had emerged during Venus's more temperate past, some organisms might have adapted to the gradually changing conditions, potentially migrating from surface oceans to atmospheric refugia as the planet's climate deteriorated. This evolutionary scenario presents tantalizing possibilities for understanding how life might respond to extreme climate change on planetary scales. The transition from surface-based to aerial existence would have required fundamental changes in cellular structure, metabolism, and behavior. Studying such adaptations could provide insights into life's resilience and its capacity for evolutionary innovation under extreme selective pressure. The isotopic composition of Venus's atmosphere provides another avenue for investigating potential biological processes. Living organisms often preferentially utilize lighter isotopes of essential elements, creating characteristic isotopic signatures in their environment. Future missions to Venus will need to measure these subtle isotopic ratios with extraordinary precision to distinguish potential biological fractionation from purely geological processes. The search for complex organic molecules in Venus's atmosphere requires instruments capable of detecting and characterizing compounds at extremely low concentrations within a highly corrosive environment. Mass spectrometry techniques adapted for Venus missions must operate reliably despite the challenging conditions, providing detailed molecular analysis during the brief time available for atmospheric sampling. These technological demands have driven innovations in miniaturization and ruggedization that benefit numerous other scientific applications. The data analysis challenges associated with Venus missions reflect the complexity of interpreting chemical signatures in an environment where biological and non-biological processes might produce similar results. Advanced pattern recognition algorithms are being developed to identify subtle correlations in atmospheric data that might reveal the presence of organized chemical processes characteristic of biological activity. These computational approaches must account for the vast number of possible chemical reactions and their potential products in Venus's unique atmospheric environment. The role of trace elements in Venus's atmospheric chemistry adds another layer of complexity to life detection efforts. Terrestrial life requires numerous trace elements for essential biological processes, and the availability of these elements in Venus's atmosphere might constrain the types of biochemistry that could evolve there. Future missions will need to conduct comprehensive elemental analysis to determine whether Venus's clouds contain the chemical ingredients necessary for complex biological processes. The possibility of seasonal variations in Venus's atmospheric chemistry introduces temporal dynamics that complicate both mission planning and data interpretation. While Venus's slow rotation creates extreme seasonal patterns unlike anything experienced on Earth, subtle changes in atmospheric circulation and chemistry might occur over timescales that affect the distribution and concentration of potential biosignatures. Understanding these temporal variations will be crucial for designing missions that can distinguish between transient phenomena and persistent biological signatures. The development of contamination protocols for Venus missions presents unique challenges given the planet's extreme conditions. Unlike Mars missions, where forward contamination by terrestrial microbes is a primary concern, Venus's hostile environment essentially sterilizes any arriving spacecraft. However, reverse contamination considerations still apply, as atmospheric samples returned to Earth must be handled with appropriate precautions to preserve their scientific integrity and prevent contamination of terrestrial environments. The emergence of artificial intelligence in astrobiology has particular relevance for Venus exploration, where the limited communication windows and extreme environmental conditions require autonomous decision-making capabilities. Future Venus missions might carry AI systems capable of adapting their sampling strategies based on real-time analysis of atmospheric conditions, maximizing the scientific return from brief encounters with the planet's atmosphere. The study of Venus's atmospheric dynamics provides crucial context for interpreting potential biological signatures. The planet's global circulation patterns transport chemical compounds across vast distances and between different atmospheric layers, potentially mixing biosignatures with purely geological or photochemical products. Understanding these circulation patterns will be essential for tracing the origins of interesting chemical signatures detected in Venus's atmosphere. The potential for discovering extinct rather than extant life in Venus's atmosphere adds another dimension to exploration strategies. Even if no living organisms currently exist in Venus's clouds, the chemical remnants of past biological activity might persist in the form of complex organic molecules or distinctive isotopic signatures. These chemical fossils could provide evidence of ancient biological processes, while informing our understanding of how life might respond to extreme environmental changes. The implications of Venus exploration extend beyond astrobiology to encompass broader questions about planetary evolution and climate stability. Understanding how Venus transformed from a potentially habitable world to its current extreme state provides crucial insights for evaluating the long-term stability of planetary climates throughout the universe. This knowledge directly informs our assessment of exoplanetary habitability and the potential longevity of biospheres on other worlds. The technological spin-offs from Venus exploration continue to find applications in terrestrial science and industry. Materials designed to withstand Venus's corrosive atmosphere have potential applications in chemical processing, while miniaturized instruments developed for Venus missions contribute to environmental monitoring and industrial quality control on Earth. The extreme engineering challenges posed by Venus drive innovations that benefit numerous other fields. As we approach this unprecedented period of Venus exploration, the scientific community is preparing for discoveries that could fundamentally alter our understanding of life in the universe. The convergence of multiple missions, advanced analytical techniques, and sophisticated theoretical frameworks creates an opportunity to answer questions that have puzzled scientists for decades. Whether these investigations ultimately reveal signs of life or exotic chemistry, they will expand our appreciation for the remarkable diversity of processes that occur on planets throughout the cosmos. The philosophical implications of our Venus exploration efforts remind us that the search for life is ultimately a search for understanding our own place in the universe. Each mission we launch, each measurement we make, each hypothesis we test, brings us closer to answering fundamental questions about the nature of existence and the potential for life to emerge and persist. under conditions radically different from those we experience on Earth. The night sky above you contains Venus somewhere in its vast expanse, whether visible as a brilliant evening star or hidden behind Earth's bulk as it travels its eternal orbit around our shared sun. Within that bright point of light lies a world of extraordinary complexity and potential, a laboratory for understanding how planets evolve and whether life might exist in forms we've never imagined. As these missions prepare to unlock Venus's secrets, we stand witness to one of the most ambitious scientific endeavors in human history. The search for life on Venus represents our species' relentless curiosity about the cosmos and our determination to explore even the most challenging environments in pursuit of knowledge. In the acidic clouds of our neighboring world, we might discover not just new forms of life, but new ways of understanding what it means to be alive in a universe filled with infinite possibilities. The data streaming back from these Venus missions will tell stories written in molecular signatures and chemical gradients, narratives of planetary evolution and potential biological innovation that have unfolded over billions of years. Each measurement adds another piece to the vast puzzle of planetary science. Another clue in our investigation of life's potential to emerge and thrive in the most unlikely places. Tonight, as you drift towards sleep, carried by the gentle rhythm of your breathing, remember that somewhere above the cloud tops of a world wreathed in sulfuric acid mist, the answers to some of humanity's most profound questions might be floating through alien skies, waiting for our instruments to find them and our minds to comprehend their significance. The universe continues its ancient dance of chemistry and possibility, and we are privileged to witness this cosmic choreography from our small blue world, reaching across the void with our curiosity and our hope, seeking kinship among the stars. The story of Venus exploration extends into realms that challenge not just our technology, but our very imagination of what constitutes a living world. As we peer deeper into the mysteries of our cloud-shrouded neighbor, we encounter questions that push against the boundaries of biology itself, forcing us to reconsider fundamental assumptions about life that have guided scientific thinking for generations. Consider the extraordinary possibility that Venus's atmosphere might harbor not just individual organisms, but entire ecosystems suspended in perpetual flight. These aerial communities would exist in a state of constant motion, their members drifting through chemical gradients and temperature zones in patterns we can barely begin to comprehend. Unlike Earth's surface-bound ecosystems, where organisms can establish territories and build lasting structures, life in Venus's atmosphere would need to adapt to an existence of eternal wandering through three-dimensional space. The energy flows in such an ecosystem would follow pathways entirely alien to terrestrial biology. On Earth, most ecosystems ultimately depend on photosynthesis, with plants capturing solar energy and converting it into chemical forms that support complex food webs. But in Venus's dimly lit cloud layers, where sulfuric acid droplets scatter and absorb much of the incoming sunlight, any photosynthetic processes would need to operate with remarkable efficiency, perhaps utilizing wavelengths of light that Earth's plants cannot access. More intriguingly, chemosynthetic pathways might dominate these hypothetical aerial ecosystems. The complex chemistry of Venus's atmosphere provides numerous opportunities for organisms to extract energy from chemical reactions rather than sunlight. Sulfur compounds, which exist in abundance throughout Venus's atmospheric layers, could serve as the foundation for entirely novel metabolic pathways. Organisms might have evolved to process sulfur dioxide, hydrogen sulfide, or even sulfuric acid itself as energy sources, creating metabolic networks unlike anything we observe in terrestrial environments. The seasonal dynamics of Venus present another fascinating dimension for potential atmospheric life. While Venus's incredibly slow rotation creates day-night cycles that last for months, these extended periods might drive atmospheric circulation patterns that create predictable migrations of nutrients and energy sources. Hypothetical aerial organisms might have evolved to follow these circulation patterns, timing their reproductive cycles and metabolic activities to coincide with favorable atmospheric conditions. The vertical stratification of Venus's atmosphere creates distinct ecological zones, each with its own unique chemistry and physical conditions. The upper haze layers might harbor organisms adapted to the most extreme acidity levels, while the middle cloud deck could support more diverse communities where temperature and pressure conditions are more moderate. The lower atmospheric regions, approaching the hellish surface conditions, might serve as boundary zones where specialized extremophiles process materials exchanged between the surface and the atmosphere above. These atmospheric layers could function like the ocean's depth zones on Earth, with different species adapted to specific pressure ranges and chemical compositions. Deep atmospheric specialists might process heavy molecules that settle from higher altitudes, while surface layer organisms take advantage of the more volatile compounds that rise from the depths. The constant vertical mixing in Venus's atmosphere would transport nutrients and waste products between these zones, creating complex biogeochemical cycles that operate entirely in gaseous phases. The reproductive strategies required for survival in this three-dimensional environment would demand evolutionary innovations beyond anything we observe on Earth. Without solid surfaces for egg-laying or nest-building, aerial organisms would need to develop entirely novel approaches to reproduction and offspring care. Perhaps they might form temporary reproductive aggregations, creating brief but complex social structures that dissolve once their reproductive function is complete. Alternatively, these organisms might have evolved broadcast reproductive strategies, releasing reproductive cells into atmospheric currents to drift until they encounter suitable conditions for development. The vast scale of Venus's atmosphere would provide enormous space for such reproductive dispersal, potentially allowing species to maintain genetic diversity across global populations, despite the challenges of finding mates in the endless expanse of cloud and mist. The sensory adaptations required for navigation in Venus's atmospheric environment would likely surpass anything we can imagine based on terrestrial examples. These organisms might have evolved exquisite chemical sensing capabilities, detecting minute changes in acidity, temperature, and atmospheric composition that guide their movements through favorable zones. They could potentially sense the subtle pressure waves created by atmospheric circulation patterns, using these cues to maintain position within optimal environmental conditions. Some species might have developed echolocation abilities adapted for the dense Venusian atmosphere, using sound waves to navigate through the murky, acidic environment where visual cues are severely limited. Others might rely on electromagnetic sensing, detecting the electrical fields generated by atmospheric chemistry, or even the planet's magnetic interactions with solar wind. The evolutionary history that could have produced such remarkable adaptations raises profound questions about Venus's climatic past and the resilience of life under extreme environmental change. Current planetary models suggest that Venus maintained much more hospitable conditions for billions of years, potentially supporting liquid water oceans and moderate surface temperatures before the runaway greenhouse effect transformed it into the extreme world we observe today. If life had emerged during Venus's more temperate past, the gradual transition to current conditions would have created intense selective pressure for organisms capable of surviving increasingly hostile environments. Some lineages might have migrated from surface waters to atmospheric refugia as oceans evaporated and surface temperatures climbed beyond the tolerance limits of most biological systems. This migration from aquatic to aerial existence would have required fundamental changes in cellular architecture, metabolic pathways, and reproductive strategies. The organisms that successfully made this transition would represent one of the most remarkable evolutionary achievements in the solar system, demonstrating life's capacity for innovation and adaptation under the most extreme circumstances imaginable. The chemical signatures left by such evolutionary processes might persist in Venus's current atmosphere, providing clues about ancient biological activity, even if no organisms currently survive in the clouds. Isotopic ratios in atmospheric gases could preserve evidence of biological fractionation that occurred millions or billions of years ago. Complex organic molecules might represent the molecular fossils of extinct organisms, chemical remnants that tell stories of life's brief flowering in Venus's ancient, more hospitable environment. The search for these molecular fossils requires analytical techniques of extraordinary sensitivity and specificity. Future Venus missions will need to distinguish between organic compounds produced by ancient biological processes and those created by ongoing geological or photochemical activity. This challenge pushes the boundaries of analytical chemistry, demanding instruments capable of detecting and characterizing trace compounds in one of the most hostile environments in the solar system. The temporal dynamics of atmospheric chemistry on Venus add another layer of complexity to these investigations. Chemical signatures might vary with Venus's extended day-night cycle, as different photochemical processes dominate during the planet's months-long periods of continuous darkness or sunlight. Understanding these temporal variations will be crucial for interpreting data collected during brief mission encounters with Venus's atmosphere. The role of atmospheric turbulence and mixing in distributing potential biosignatures throughout Venus's atmosphere presents both opportunities and challenges for detection efforts. Vigorous circulation patterns could spread biological signatures across vast regions, increasing the probability that atmospheric probes will encounter evidence of biological activity. However, this same mixing could dilute biosignatures below detection limits or combine them with geological signatures in ways that complicate interpretation. The development of increasingly sophisticated computational models allows scientists to simulate these complex atmospheric processes and predict how biological signatures might behave in Venus's dynamic environment. These models incorporate everything from photochemical reactions driven by solar radiation to thermodynamic processes caused by temperature gradients, creating comprehensive frameworks for interpreting observational data. Machine learning approaches are becoming increasingly important for analyzing the vast datasets that Venus missions will generate. These computational methods can identify subtle patterns in atmospheric chemistry that might escape human analysis, potentially revealing biosignatures embedded within larger datasets of chemical measurements. Neural networks trained on laboratory simulations of Venus-like conditions can learn to recognize the characteristic signatures of biological versus non-biological processes. The international collaboration surrounding Venus exploration has created unprecedented opportunities for sharing data, techniques, and insights across national boundaries and institutional barriers. Scientists from around the world are contributing their expertise to mission design, instrument development, and data analysis, ensuring that the most advanced capabilities available are brought to bear on these challenging investigations. The technological innovations driven by Venus exploration continue to find applications far beyond planetary science. Materials designed to withstand sulfuric acid corrosion have potential uses in chemical processing industries, while miniaturized analytical instruments developed for space missions contribute to environmental monitoring and medical diagnostics on Earth. The extreme engineering challenges posed by Venus drive technological advances that benefit numerous fields. The philosophical implications of discovering life in Venus's atmosphere would extend far beyond confirming the existence of extraterrestrial organisms. Such a discovery would demonstrate that life can emerge and persist under conditions so extreme that they challenge our most basic assumptions about habitability. It would suggest that the universe might be teeming with life forms so alien that we lack the conceptual frameworks to understand them. The biochemical innovations required for survival in Venus's acidic atmosphere could inspire entirely new approaches to biotechnology and materials science. Organisms capable of thriving in concentrated sulfuric acid might possess cellular mechanisms and molecular structures that could revolutionize our understanding of biochemistry. These discoveries could lead to new medical treatments, industrial processes, or environmental remediation techniques based on principles learned from Venusian extremophiles. The search for life on Venus also serves as a crucial testing ground for the techniques and technologies we'll need to investigate potentially habitable exoplanets. The challenges of detecting biosignatures in Venus's atmosphere mirror those we face when analyzing the atmospheric composition of planets orbiting distant stars. Success in characterizing Venus's atmospheric chemistry will demonstrate our readiness to interpret similar data from exoplanetary observations. The ongoing development of more sensitive detection methods promises to revolutionize our ability to search for life throughout the solar system and beyond. Techniques pioneered for Venus missions could be adapted for studying the subsurface oceans of icy moons, the methane lakes of Titan, or the ancient geological formations of Mars. Each technological advancement brings us closer to answering the fundamental question of whether life exists beyond Earth. As we stand on the threshold of this new era in Venus exploration, we're reminded that the greatest discoveries often emerge from the most unexpected places. Venus, dismissed for decades as utterly hostile to life, now represents one of the most promising frontiers in astrobiology. The planet that once exemplified the limits of habitability now expands our understanding of where life might exist, challenging us to think beyond our terrestrial assumptions about what organisms require to survive and flourish. The missions preparing to explore Venus carry with them the accumulated knowledge and hopes of generations of scientists who have wondered about life beyond Earth. They represent humanity's relentless curiosity and our determination to explore even the most challenging environments in pursuit of understanding. Whether these missions ultimately discover signs of life or reveal new forms of exotic chemistry, they will transform our comprehension of Venus and expand our appreciation for the remarkable diversity of worlds that exist within our cosmic neighborhood. Tonight, as Venus traces its eternal path across the star-scattered darkness above, its brilliant presence serves as a beacon calling us toward discovery. Within those swirling acidic clouds lie answers to questions that have haunted human imagination since we first looked up and wondered whether we are alone. The search for life on Venus embodies our species' greatest aspirations, our willingness to reach across the vast emptiness of space with instruments and imagination, seeking connection and understanding in the infinite mystery of existence. As you rest here in the gentle embrace of evening, remember that you are witnessing the dawn of a new chapter in humanity's cosmic story. The missions launching toward Venus in the coming years will carry our questions and hopes across millions of miles of void, seeking answers in the most unlikely of places. In the acidic mists of our neighboring world, we might discover not just new forms of life, but new ways of understanding what it means to be alive in a universe filled with endless possibilities and eternal wonder. The profound implications of Venus exploration extend into realms that challenge our most fundamental understanding of planetary habitability and the conditions necessary for life to emerge and persist. As we prepare to peer deeper into the mysteries of our cloud-shrouded neighbor, we encounter questions that stretch across disciplines, connecting atmospheric chemistry to evolutionary biology, planetary science to philosophy, and engineering innovation to the deepest mysteries of existence itself. Consider the extraordinary chemical orchestra playing out in Venus's atmospheric layers, where countless molecular interactions unfold in patterns we're only beginning to appreciate. Each chemical reaction in those acidic clouds represents a note in a vast symphony of atmospheric processes, some driven by solar radiation, others by the planet's internal heat, and still others by the complex interplay between surface geology and atmospheric dynamics. Within this chemical symphony, the potential signatures of biological activity would need to be distinguished from the overwhelming background of purely geological and photochemical processes. The challenge of identifying biological signatures in such a complex chemical environment requires us to develop entirely new approaches to astrobiology. Traditional methods of life detection, refined through decades of terrestrial microbiology research, must be adapted to function in conditions so extreme that they push the boundaries of what we consider possible. The instruments being designed for Venus missions represent marvels of miniaturization and ruggedization, capable of operating reliably in environments that would instantly destroy most terrestrial technology. The time constraints imposed by Venus exploration add urgency to every aspect of mission design and data collection. Unlike Mars rovers that can leisurely examine rocks and soil for months or years, Venus missions must accomplish their scientific objectives during brief encounters measured in minutes or hours. This temporal pressure demands unprecedented efficiency in data collection and analysis, requiring instruments that can make critical measurements and transmit results before succumbing to the planet's hostile environment. The data compression techniques developed for Venus missions reflect the extreme communication challenges posed by interplanetary distances and limited transmission windows. Every bit of information transmitted from Venus to Earth must be carefully prioritized and encoded to maximize scientific value within severe bandwidth constraints. Advanced algorithms compress complex atmospheric measurements into data packages small enough to traverse the vast emptiness between worlds, carrying precious cargo of scientific discovery across the solar system. The atmospheric circulation patterns on Venus create a dynamic environment where chemical signatures are constantly being mixed, transported, and transformed. Understanding these circulation patterns becomes crucial for interpreting any biosignatures that might be detected, as the location where a measurement is made might be far removed from the original source of the chemical signature. Atmospheric modeling has become an essential tool for tracing the origins of chemical signatures and understanding how they might be distributed throughout Venus's global atmospheric system. The seasonal variations in Venus's atmospheric chemistry, driven by the planet's extraordinarily slow rotation, create temporal dynamics unlike anything experienced on Earth. These extended seasons might influence the distribution and concentration of atmospheric chemicals in ways that affect both the likelihood of detecting biosignatures and the interpretation of any signatures that are found. Future missions will need to account for these temporal variations when planning their observation strategies and analyzing their results. The potential for discovering not just life, but entire ecosystems in Venus's atmosphere opens up fascinating possibilities for understanding how biological communities might organize and function in three-dimensional space. Unlike terrestrial ecosystems anchored to solid surfaces, aerial ecosystems would exist in constant motion, their structure and function determined by atmospheric currents, chemical gradients, and the vertical stratification of Venus's atmospheric layers. The energy flows in such ecosystems would follow patterns entirely alien to our Earth-based experience. Primary producers might harvest energy from chemical reactions rather than sunlight, creating the foundation for food webs based on chemosynthesis rather than photosynthesis. The efficiency of energy transfer in such systems would be constrained by the availability of chemical substrates and the harsh environmental conditions, potentially leading to highly specialized organisms with metabolic pathways unlike anything we observe in terrestrial biology. The reproductive strategies required for survival in Venus's atmospheric environment would demand evolutionary innovations that stretch our understanding of biological possibility. Without solid surfaces for attachment or shelter, organisms would need to develop entirely novel approaches to mating, reproduction, and offspring care. Perhaps they might form temporary aggregations during reproductive periods, creating brief but complex social structures that serve specific biological functions before dissolving back into the general population. The sensory adaptations necessary for navigation in Venus's three-dimensional atmospheric environment would likely surpass anything we observe in terrestrial organisms. Chemical sensing capabilities would need to be extraordinarily sophisticated to detect the subtle gradients and variations that could guide organisms toward favorable conditions. Pressure sensing might allow organisms to detect atmospheric circulation patterns and position themselves advantageously within the constantly moving aerial environment. The evolutionary history that could have produced such remarkable adaptations raises profound questions about Venus's past climate and the potential for life to persist through extreme environmental transitions. If Venus once maintained more hospitable conditions, the gradual shift toward current extremes would have created intense selective pressure for organisms capable of surviving in increasingly challenging environments. The evolutionary innovations required for this transition would represent one of the most remarkable examples of adaptation in the known universe. The molecular fossils that might persist from ancient Venusian life could provide windows into biological processes that occurred billions of years ago, when Venus might have been a very different world. These chemical remnants would tell stories of evolutionary adaptation, metabolic innovation, and the ultimate limits of biological resilience. Detecting and interpreting such molecular fossils requires analytical techniques of extraordinary sensitivity and specificity. The isotopic signatures left by biological processes could persist in Venus's atmosphere long after the organisms themselves have vanished. Living systems often preferentially utilize lighter isotopes of essential elements, creating characteristic isotopic ratios that can be measured with sophisticated mass spectrometry techniques. Future Venus missions will search for these subtle isotopic signatures as potential evidence of past or present biological activity. The role of trace elements in Venus's atmospheric chemistry adds another layer of complexity to life detection efforts. Biological processes require numerous trace elements for essential functions, and the availability of these elements in Venus's atmosphere might constrain the types of biochemistry that could evolve there. Comprehensive elemental analysis will be necessary to determine whether Venus's atmospheric chemistry could support the complex molecular processes associated with life. The development of contamination protocols for Venus missions presents unique challenges given the planet's extreme sterilizing conditions. While forward contamination by terrestrial organisms is unlikely given Venus's hostile environment, reverse contamination protocols must still be considered for any samples that might eventually be returned to Earth. These protocols ensure that scientific integrity is maintained while protecting both terrestrial and potentially Venusian biological systems. The emergence of artificial intelligence in planetary exploration has particular relevance for Venus missions, where communication delays and extreme environmental conditions require autonomous decision-making capabilities. Future missions might carry AI systems capable of adapting their sampling strategies based on real-time analysis of atmospheric conditions, optimizing scientific return during brief encounter windows with Venus's atmosphere. The comparative planetology insights gained from Venus exploration extend far beyond questions of habitability to encompass fundamental processes of planetary evolution and climate dynamics. Understanding how Venus evolved from a potentially habitable world to its current extreme state provides crucial context for evaluating the long-term stability of planetary climates throughout the universe. These insights directly inform our assessment of exoplanetary habitability and the factors that determine whether worlds can maintain conditions suitable for life over geological timescales. The technological innovations driven by Venus exploration continue to find applications across numerous fields beyond planetary science. Materials designed to withstand sulfuric acid corrosion have potential applications in chemical processing industries, while miniaturized analytical instruments developed for space missions contribute to environmental monitoring and industrial quality control on Earth. The extreme engineering challenges posed by Venus drive technological advances that benefit society in ways far removed from space exploration. The international collaboration surrounding Venus exploration reflects the global significance of this scientific endeavor and the shared human interest in understanding our place in the universe. Scientists from around the world contribute their expertise to mission design, instrument development, and data analysis, ensuring that the most advanced capabilities available are brought to bear on these challenging investigations. This collaborative approach maximizes the scientific return while fostering international cooperation in the pursuit of knowledge. The educational impact of Venus exploration extends beyond the scientific community to inspire new generations of researchers, engineers, and explorers. The technical challenges and potential discoveries associated with Venus missions provide compelling examples of how scientific curiosity drives technological innovation and expands human knowledge. Students and young professionals drawn to these challenges will carry forward the tradition of exploration and discovery that defines our species. The philosophical implications of Venus exploration touch on fundamental questions about the nature of life, the conditions necessary for its emergence, and our understanding of habitability in the universe. Whether or not we ultimately discover life in Venus's clouds, the process of searching challenges our assumptions and expands our conceptual frameworks for understanding biological possibility. These philosophical dimensions of exploration are as important as the technical achievements they inspire. The long-term vision for Venus exploration extends beyond current mission plans to encompass more ambitious concepts for studying the planet's atmosphere and potential biology. Future missions might deploy networks of atmospheric probes to study chemical variations across different regions and atmospheric layers. Advanced orbital platforms could provide long-term monitoring of atmospheric dynamics and chemistry, building comprehensive data sets that reveal temporal patterns and seasonal variations. The possibility of eventually establishing permanent research platforms in Venus's atmosphere, while technically challenging, represents an intriguing long-term goal that could revolutionize our understanding of the planet and its potential for harboring life. Such platforms would require breakthrough advances in materials, science, power systems, and life support technologies. But they could provide unprecedented opportunities for detailed study of Venus's atmospheric chemistry and dynamics. The search for life on Venus embodies humanity's relentless curiosity about our cosmic environment and our determination to explore even the most challenging frontiers in pursuit of understanding. Each mission launched toward Venus, each measurement made in its hostile atmosphere, each analysis of its complex chemistry contributes to our growing comprehension of planetary science and the potential for life to exist in environments radically different from Earth. The convergence of multiple Venus missions in the coming decade creates an unprecedented opportunity for comprehensive study of our neighboring world. The combined observations from atmospheric probes, orbital surveys, and ground-based telescopes will provide a multifaceted view of Venus that reveals its secrets from multiple perspectives simultaneously. This coordinated approach represents a fundamental shift in how we explore other worlds, moving beyond single-mission investigations to comprehensive, multi-platform campaigns. As we approach this remarkable period in Venus exploration, we stand witness to one of the most ambitious scientific endeavors in human history. The questions we're asking about Venus's atmospheric chemistry and potential habitability represent some of the most profound inquiries our species has ever undertaken. The answers we discover will shape our understanding of life's possibilities throughout the universe and inform our continuing search for our place in the cosmic order. The night sky above holds Venus somewhere in its star-scattered expanse, sometimes visible as our brilliant morning or evening star, sometimes hidden behind Earth's bulk as it follows its orbital dance around our shared sun. Within that shining point of light lies a world of extraordinary complexity and mystery, a natural laboratory where extreme chemistry unfolds according to physical laws that govern planetary atmospheres throughout the universe. The atmospheric chemistry of Venus continues its ancient dance of molecular interactions and chemical transformations, processes that have operated for billions of years and will continue long after our current missions have completed their investigations. Whether these processes include biological components remains one of the most compelling questions facing modern science, a mystery that draws us across the vast emptiness of space with our instruments and imagination. Tonight, as you rest in the gentle embrace of your terrestrial environment, remember that humanity stands on the threshold of potentially answering one of our most fundamental questions about our cosmic neighborhood. The missions preparing to explore Venus carry with them the accumulated knowledge and aspirations of countless scientists, engineers, and dreamers who have wondered about life beyond Earth. In the swirling, acidic clouds of our neighboring world, we might discover not just new forms of life, but entirely new ways of understanding what it means to be alive in a universe filled with possibilities we've barely begun to imagine. The search for life on Venus represents our species' greatest scientific adventure, our willingness to reach across the cosmic void with curiosity and hope, seeking answers to questions that have haunted human imagination since we first looked up at the stars and wondered whether we are alone. The search for life on Venus also represents a profound shift in how we conceptualize the boundaries of habitability itself. For generations, scientists have relied on concepts like the Goldilocks zone, that narrow band around stars where temperatures are just right for liquid water to exist on planetary surfaces. But Venus challenges these traditional notions, suggesting that habitability might extend into realms we never thought to explore. The temperate cloud layers floating high above Venus's hellish surface create a kind of aerial Goldilocks zone, suspended in the sky like islands of possibility in an ocean of extremes. This expanded understanding of habitability has implications that reach far beyond our solar system. If life can exist in the atmospheric layers of Venus, then countless worlds throughout the galaxy might harbor aerial biospheres that we've never thought to consider. Gas giant planets, with their vast atmospheric layers and complex chemistry, suddenly become potential habitats rather than barren wastelands. The number of potentially habitable worlds in our universe expands exponentially when we consider three-dimensional atmospheric environments rather than just planetary surfaces. The biochemical innovations that would be required for life in Venus's clouds push against the very foundations of what we understand about living systems. Traditional biochemistry relies on water as the universal solvent, the medium in which all of life's essential reactions take place. But in Venus's sulfuric acid environment, hypothetical organisms would need to have evolved entirely different approaches to cellular chemistry. Perhaps they use concentrated acid as their primary solvent, developing molecular machinery that not only tolerates but requires these extreme conditions. The cellular structures of potential Venusian life forms would need to be fundamentally different from anything we observe on Earth. Instead of lipid membranes that would instantly dissolve in sulfuric acid, These organisms might have evolved protective barriers made from entirely novel molecular frameworks. Their internal chemistry might operate according to principles we've never encountered, utilizing chemical pathways that seem impossible from our terrestrial perspective. Consider the extraordinary challenge of maintaining water balance in such an environment. Any hypothetical organisms in Venus's atmosphere would need to concentrate and conserve water at levels hundreds of times greater than the surrounding environment. This might require specialized cellular compartments or molecular pumps that can extract trace amounts of water vapor from the acidic atmosphere and maintain it at biologically useful concentrations. Such adaptations would represent evolutionary innovations beyond anything we've documented in terrestrial extremophiles. The energy metabolism of aerial Venusian life presents equally fascinating puzzles. With limited solar radiation penetrating the thick cloud layers, photosynthesis as we know it would be extremely inefficient. Instead, these organisms might have evolved to harvest energy from the rich chemistry of the atmosphere itself. Sulfur compounds could serve as both energy sources and building blocks for biological structures, creating metabolic pathways that are simultaneously alien and elegant in their adaptation to local conditions. The atmospheric dynamics of Venus create a constantly changing environment that would challenge any life forms attempting to maintain stable populations. The planet's global circulation patterns transport chemical compounds across vast distances, creating gradients and mixing zones that could either support or disrupt biological communities. Organisms would need to be remarkably adaptable, capable of thriving in conditions that change continuously as atmospheric currents carry them through different chemical and physical zones. The vertical stratification of Venus's atmosphere creates distinct environmental niches that might support specialized biological communities. Near the top of the cloud layers, where acidity is most extreme and temperatures are cooler, we might find highly specialized organisms adapted to the most challenging conditions. In the middle altitudes, where temperatures and pressures are more moderate, diverse communities might flourish in relative abundance. The lower atmospheric regions, approaching the surface, could harbor organisms specialized for high temperature, high pressure conditions that would be lethal to species from higher altitudes. These atmospheric ecosystems would exist in perpetual motion, their inhabitants carried by winds and circulation patterns across global distances. Unlike terrestrial ecosystems with defined geographical boundaries, aerial ecosystems would be fluid and dynamic, their composition and structure constantly shifting as organisms are transported through different atmospheric zones. This mobility could facilitate genetic exchange across vast populations, while creating challenges for maintaining stable ecological relationships. The reproductive cycles of atmospheric organisms would need to be precisely timed to take advantage of favorable conditions that might occur only briefly or seasonally. Perhaps these organisms have evolved to synchronize their reproductive activities with Venus's extended day-night cycles, timing critical life history events to coincide with optimal atmospheric conditions. The vast scale of Venus's atmosphere would provide ample space for reproductive dispersal, but finding mates and suitable conditions for development would require sophisticated behavioral and physiological adaptations. The sensory world of potential Venusian life forms would be utterly alien to our terrestrial experience. In the dim, hazy environment of Venus's clouds, visual systems would need to operate in very different wavelengths of light, perhaps detecting infrared radiation or chemical luminescence rather than the visible spectrum we're familiar with. Chemical sensing would likely be extraordinarily sophisticated, allowing organisms to navigate complex gradients of acidity, temperature, and atmospheric composition. The social behaviors that might evolve among aerial organisms present fascinating possibilities for speculation. Without territories to defend or permanent structures to build, social organization would need to be based on different principles entirely. Perhaps organisms form temporary aggregations that serve specific functions before dispersing back into the general population. Or maybe complex signaling systems allow individuals to maintain contact across vast atmospheric distances, creating social networks that span continents. The geological connections between Venus's surface and its atmospheric chemistry add another layer of complexity to the search for life. Volcanic activity continues to inject gases and particles into the atmosphere, creating chemical inputs that could either support or inhibit biological processes. Understanding these geological contributions becomes crucial for distinguishing between biological and non-biological sources of atmospheric chemistry. The interaction between Venus's active geology and its atmospheric chemistry creates a dynamic system where surface processes influence conditions throughout the entire atmospheric column. The temporal evolution of Venus's atmospheric composition over geological timescales provides context for understanding how life might have emerged and persisted through changing conditions. Venus's atmosphere today is dramatically different from what it might have been billions of years ago, when the planet potentially maintained more hospitable surface conditions. Any life that might exist in today's atmosphere could be the evolutionary descendants of organisms that adapted to gradually changing conditions as Venus transformed into its current extreme state. The isotopic chemistry of Venus's atmosphere offers another avenue for investigating potential biological processes. Living organisms often fractionate isotopes in characteristic ways, creating signatures that can persist long after the organisms themselves have vanished. Future missions will need to measure isotopic ratios with extraordinary precision to distinguish potential biological fractionation from purely geological or atmospheric processes. These measurements require instruments of remarkable sensitivity and accuracy, capable of detecting minute variations in isotopic composition within the complex chemical matrix of Venus's atmosphere. The role of atmospheric turbulence in mixing and distributing chemical signatures throughout Venus's atmosphere presents both opportunities and challenges for biosignature detection. Vigorous mixing could spread biological signatures across large regions, increasing the probability that atmospheric probes will encounter evidence of life. However, this same mixing could dilute biosignatures below detection limits or combine them with geological signatures in ways that complicate interpretation. The development of next-generation analytical techniques specifically for Venus exploration pushes the boundaries of what's possible in planetary science instrumentation. Mass spectrometers, designed to operate in sulfuric acid environments, must be constructed from materials that can withstand extreme corrosion while maintaining analytical precision. Optical instruments need to function in the dim, hazy conditions of Venus's clouds, while distinguishing between biological and non-biological fluorescent signatures. The data processing challenges associated with Venus missions require innovative approaches to extracting scientific information from limited datasets. Machine learning algorithms trained on laboratory simulations of Venus-like conditions can learn to recognize subtle patterns that might indicate biological activity. These computational methods must operate within the severe constraints imposed by limited communication bandwidth and brief mission durations, making every bit of transmitted data precious. The international scientific collaboration surrounding Venus exploration reflects the global significance of this endeavor and the shared human interest in understanding our place in the universe. Research teams from around the world contribute their expertise to mission design, instrument development, and data analysis, ensuring that the most advanced capabilities are brought to bear on these challenging investigations. This collaborative approach maximizes scientific return while fostering international cooperation in the pursuit of knowledge. The educational and inspirational impact of Venus exploration extends far beyond the scientific community to capture the imagination of students, educators, and the general public. The technical challenges and potential discoveries associated with Venus missions provide compelling examples of how scientific curiosity drives technological innovation and expands human understanding. These missions inspire new generations of scientists, engineers, and explorers who will carry forward humanity's tradition of reaching toward the unknown. The philosophical dimensions of searching for life on Venus touch on fundamental questions about the nature of existence and our understanding of what it means to be alive. Even if no life is ultimately discovered in Venus's atmosphere, the process of searching challenges our assumptions and expands our conceptual frameworks for understanding biological possibility. These philosophical implications are as significant as any technical discoveries that might emerge from Venus exploration. The long-term vision for Venus exploration encompasses increasingly sophisticated missions that could revolutionize our understanding of atmospheric chemistry and potential biology. Future concepts include networks of atmospheric monitoring stations, advanced orbital platforms for long-term observation, and even ambitious ideas for floating research facilities that could maintain position in Venus's temperate cloud layers for extended periods. While technically challenging, such missions could provide unprecedented opportunities for detailed study of Venus's atmospheric dynamics and chemistry. The technological innovations driven by Venus exploration continue to find applications across numerous fields beyond planetary science. Advanced materials designed to withstand sulfuric acid corrosion have potential uses in chemical processing industries, while miniaturized analytical instruments developed for space missions contribute to environmental monitoring and medical diagnostics on Earth. The extreme engineering challenges posed by Venus drive technological advances that benefit society in unexpected ways. The search for life on Venus represents one of the most ambitious scientific endeavors in human history, embodying our species' relentless curiosity about the cosmic environment and our determination to explore even the most challenging frontiers. Each mission launched toward Venus, each measurement made in its hostile atmosphere, each analysis of its complex chemistry contributes to our growing understanding of planetary science and the potential for life to exist in environments radically different from Earth. As we prepare for this unprecedented period of Venus exploration, we stand witness to a convergence of scientific capability, technological innovation, and human curiosity that could answer some of our most profound questions about life in the universe. The The missions launching in the coming years carry with them the hopes and dreams of countless individuals who have wondered about our cosmic neighborhood and our place within it. The atmospheric chemistry of Venus continues its ancient dance of molecular interactions and transformations, processes that have operated for billions of years according to the fundamental laws that govern planetary atmospheres throughout the universe. Whether these processes include biological components remains one of the most compelling mysteries facing modern science, drawing us across the vast emptiness of space with our instruments and imagination. Tonight, as Venus traces its eternal path through the star-scattered darkness above, remember that you are witnessing the beginning of a new chapter in humanity's cosmic story. Within those brilliant, cloud-wrapped mysteries lie answers to questions that have haunted our species since we first looked up and wondered about the nature of existence itself. The search for life on Venus embodies our greatest aspirations, our willingness to reach beyond the familiar boundaries of our world, seeking understanding in the infinite expanse of possibility that surrounds us. In the gentle quiet of this moment, as you rest beneath the same stars that illuminate Venus's journey through space, know that the universe continues its magnificent dance of chemistry and physics, time and space, mystery and revelation. Whether life exists in the acidic clouds of our neighboring world, or whether those clouds harbor only exotic chemistry, the very act of searching expands our understanding of what's possible and reminds us that we are part of something far grander and more mysterious than we can fully comprehend. The questions we ask about Venus, the missions we launch, the discoveries we make will echo through generations, shaping how future humans understand their place in the cosmic order. In reaching toward Venus with our curiosity and hope, we participate in the universe's ongoing journey towards self-awareness, adding our voices to the ancient conversation between mind and cosmos that defines our species' greatest adventure. The story of Venus exploration carries within it echoes of humanity's deepest yearnings for connection across the cosmic void. As we prepare to send our mechanical emissaries into those acidic clouds, we're not merely conducting scientific experiments. We're extending our consciousness across millions of miles of emptiness, reaching toward a world that might harbor forms of existence so alien that they challenge every assumption we've held about what it means to be alive. The instruments aboard these Venus missions represent more than sophisticated technology. They are extensions of our senses, mechanical eyes, and chemical tongues that will taste the atmosphere of another world and transmit those sensations back to us across the vast silence of space. When the Venus Lifefinder probe descends through those sulfuric acid clouds, its brief 5-minute encounter with Venus's temperate atmospheric layers will compress eons of scientific curiosity into a handful of precious measurements that could reshape our understanding of life itself. The philosophical weight of this moment in human history cannot be overstated. We stand at a threshold where the questions that have haunted our species since the dawn of consciousness might finally receive answers. The possibility that life could exist in forms so radically different from terrestrial biology forces us to confront the limits of our imagination and expand our definitions of what constitutes a living system. If organisms can thrive in the concentrated sulfuric acid environment of Venus's clouds, then the universe suddenly becomes a far stranger and more wonderful place than we ever dared to imagine. The engineering challenges faced by Venus missions reflect the profound audacity of this scientific endeavor. To design instruments capable of functioning in environments that would instantly destroy most materials requires pushing technology to its absolute limits. The fact that we can even contemplate sending sophisticated analytical equipment into Venus's hostile atmosphere speaks to the remarkable ingenuity and determination that characterizes our species' approach to understanding the unknown. The atmospheric chemistry of Venus operates according to principles that stretch across vast scales of time and space. The chemical reactions occurring in those cloud layers have been proceeding for billions of years, following the fundamental laws of physics and chemistry that governs molecular behavior throughout the universe. Whether biological processes contribute to this ancient chemical symphony remains one of the most tantalizing mysteries in modern science, a question that draws us inexorably toward Venus despite the enormous challenges involved in exploring such a hostile environment. The temporal dimensions of Venus exploration add poignancy to our search for life on this neighboring world. The brief operational lifetime of atmospheric probes means that each mission represents a fleeting opportunity to peer into mysteries that have persisted for geological ages. These mechanical visitors to Venus's clouds will experience more in their final moments than some scientific instruments accomplish in years of operation, compressed existence that mirrors the intensity of the questions they're designed to answer. The data that streams back from Venus missions will carry information encoded in electromagnetic radiation that has traveled across interplanetary distances at the speed of light. Each transmitted byte represents a fragment of Venus's atmospheric story, pieces of a vast puzzle that scientists will spend years assembling into coherent pictures of atmospheric chemistry and potential biological activity. The bandwidth limitations imposed by interplanetary communication ensure that every transmitted measurement is precious, carefully selected to maximize scientific understanding within severe technical constraints. The international collaboration surrounding Venus exploration reflects humanity's shared fascination with questions that transcend national boundaries and cultural differences. Scientists from around the world contribute their expertise to mission design and data analysis, united by curiosity about whether life might exist in forms so alien that they challenge our most fundamental assumptions about biology. This collaborative spirit embodies the best aspects of human nature, our capacity to work together in pursuit of understanding that benefits all of humanity. The atmospheric circulation patterns on Venus create a dynamic environment where chemical signatures are constantly being transported across vast distances and between different atmospheric layers. Understanding these circulation patterns becomes crucial for interpreting any biosignatures that might be detected, as the location where measurements are made might be far removed from the original sources of interesting chemical signatures. The three-dimensional nature of atmospheric mixing on Venus creates opportunities for chemical signatures to persist and spread throughout the planet's atmospheric system. The potential discovery of life in Venus's atmosphere would represent a profound expansion of our understanding of biological possibility. Such organisms would exist in perpetual motion through three-dimensional space, never experiencing the stability of solid surfaces that characterizes terrestrial life. Their entire evolutionary history would have unfolded in aerial environments, creating adaptations and survival strategies unlike anything we observe on Earth. The biochemical innovations required for survival in concentrated sulfuric acid would push the boundaries of what we consider biologically possible. The energy sources available to potential Venusian life forms present fascinating challenges that require us to think beyond terrestrial examples of metabolism and nutrition. The dim lighting conditions in Venus's cloud layers would make traditional photosynthesis extremely inefficient, potentially favoring chemosynthetic pathways that derive energy from atmospheric chemistry rather than solar radiation. The abundance of sulfur compounds in Venus's atmosphere could serve as both energy sources and building blocks for exotic forms of biochemistry. The reproductive strategies that would be necessary for survival in Venus's atmospheric environment stretch our imagination of biological possibility. Without solid surfaces for nesting or territorial establishment, aerial organisms would need to develop entirely novel approaches to finding mates, reproducing, and caring for offspring. The vast scale of Venus's atmosphere would provide enormous space for population dispersal, while creating challenges for maintaining genetic diversity and social cohesion across global populations. The sensory adaptations required for navigation in Venus's three-dimensional atmospheric environment would likely surpass anything we observe in terrestrial organisms. Chemical sensing capabilities would need to detect minute variations in atmospheric composition that could guide organisms toward favorable conditions. The ability to sense pressure variations and atmospheric circulation patterns might allow organisms to position themselves advantageously within the constantly moving aerial environment. The evolutionary history that could have produced such remarkable adaptations raises profound questions about Venus's climatic past and the potential for life to persist through extreme environmental transitions. If Venus once maintained more hospitable conditions, the gradual transformation to current extremes would have created intense selective pressure for organisms capable of surviving increasingly hostile environments. The evolutionary innovations required for this transition would represent one of the most extraordinary examples of adaptation in the known universe. The isotopic signatures that might persist in Venus's atmosphere could provide windows into ancient biological processes that occurred when Venus was a very different world. Living systems often fractionate isotopes in characteristic ways, creating chemical fingerprints that can persist long after the organisms themselves have vanished. Detecting these subtle isotopic variations requires analytical techniques of extraordinary precision and sensitivity. The molecular complexity that characterizes living systems presents both opportunities and challenges for detection in Venus's atmospheric environment. Biological processes typically create complex organic molecules that differ significantly from the simpler compounds produced by purely geological or photochemical processes. However, distinguishing between biological and non-biological sources of molecular complexity requires comprehensive understanding of all the chemical processes occurring in Venus's dynamic atmospheric system. The role of water in potential Venusian biochemistry presents one of the most fundamental challenges for understanding how life might exist in Venus's clouds. The extremely low water vapor concentrations in Venus's atmosphere would require hypothetical organisms to concentrate and conserve water at levels far exceeding anything observed in terrestrial biology. This might necessitate entirely novel cellular mechanisms for water extraction and retention. The pH extremes encountered in Venus's sulfuric acid clouds would require biological systems capable of maintaining stable internal chemistry, despite external conditions that would instantly denature most terrestrial biomolecules. The cellular structures and protective mechanisms necessary for survival in such acidic environments would need to be fundamentally different from anything we observe in Earth-based life forms. The atmospheric pressure variations encountered throughout Venus's atmospheric column create distinct environmental zones that might support different types of biological communities. The transition zones between these pressure regimes could serve as interfaces where chemical and energy exchanges occur, potentially creating ecological niches that support specialized organisms adapted to gradient conditions. The thermal environment of Venus's atmosphere presents both challenges and opportunities for potential biological systems. While surface temperatures are utterly lethal, the temperature profiles in the cloud layers create zones where thermal conditions might be compatible with exotic forms of biochemistry. Understanding these thermal gradients becomes crucial for identifying atmospheric regions where biological activity might be most likely to occur. The chemical diversity present in Venus's atmosphere creates opportunities for complex biochemical pathways that might support living systems. The variety of sulfur compounds, trace gases, and reactive species could provide the chemical building blocks necessary for biological structures and metabolic processes. However, this same chemical diversity creates analytical challenges for distinguishing biological signatures from the complex background of atmospheric chemistry. The atmospheric dynamics that govern Venus's circulation patterns create temporal variations in chemical composition and physical conditions throughout the planet's atmospheric system. These temporal changes might influence the distribution and detectability of biological signatures, requiring mission planners to consider optimal timing for atmospheric sampling and analysis. So as we reach the end of our cosmic journey together, remember that the search for life on Venus represents something profound about who we are as a species. Whether these upcoming missions discover microbial communities drifting through acidic clouds or reveal only exotic chemistry, they expand our understanding of what's possible in this vast universe. Tonight, as Venus shines somewhere in the darkness above, know that humanity stands ready to answer one of our most fundamental questions about our place among the stars. Sweet dreams, fellow cosmic explorers.